Oh boy, we have a doozy of a concept today. It's Monday, November 7th. Thanks for watching my video, ladies and gentlemen. I think you're doing fantastic. Keep following along, taking notes, trying the homework problems, asking me questions, working with your partners, all those things that are making you successful. I really appreciate it. So here's what we're talking about today. How do you take the derivative of an inverse trig function? Now, first of all, it's been a while since we've dealt with inverse trig functions. So let's talk about just the notation maybe. That little -1 means inverse, okay? It doesn't mean take the reciprocal. It's not 1 over the sine function. Like if we saw 5 to the -1, that's 1/5, right? That's not the same as sine to the -1. Sine to the -1 of x, not the same. Not the same thing. Okay? Not the same thing. Shoot, man. So what does it mean? Right? Okay, so an inverse function kind of undoes the original function. So what was the original function? Like we take the sine of some angle and it gives us a ratio. So the ratio's over here. This is the ratio. And this is the angle right in here. Okay? You might say, well, why do you have the sine of y? Well, because the inverse sine of x means x is the ratio. Right in here is the ratio. Okay, so I want to know, when I say inverse sine, I want to know what angle would have this particular ratio right in here. Now, the sine ratio is the opposite leg over the hypotenuse. Okay, so what I did is I kind of got rid of my inverse function. I said, well, if I took here's my angle over here. If I took the sine of that angle, I would get some ratio. So let's make a drawing of this. I think a drawing might help us out. And I'm just going to make my drawing in the first quadrant. You guys know you could go anywhere around the unit circle that you want to. But let's say we just had an angle in the first quadrant, okay? And here's my angle. I'm going to call it y. And I know it gets a little confusing because you might say, well, this is the y-axis and this is the x-axis. But I know it's a little crazy. Maybe we don't even need the axes on here. I could get rid of the axes. I'm going to do that. That might be a crazy idea. Okay, so I'm going to start back with just the triangle. So let's say you just had a triangle, and in your triangle, you said, here's my angle, and then this side over here is x, and let's say the hypotenuse is 1. Well, the sine of that angle, the sine of y, is x over 1. So the ratio, I guess I could make this look more like a ratio by writing it as x over 1. It's the opposite leg over the hypotenuse. So this triangle represents this situation, or this equation is represented in this triangle down here, right? So let's say I wanted the derivative of inverse sine. Okay, so I'm going to kind of go about this in a funny way. This equation here is equivalent to this equation right over here, because this is saying I want to find an angle whose sine is equal to x. That's what the inverse sine really is. I want to find an angle. So you notice I'm pointing to this notation right here, sine with a little -1. It means, in English, I want to find an angle whose ratio of the opposite leg to the hypotenuse is x. Well, here's my angle right here. I got an angle right there drawn for you. Okay, so look at the drawing. I'm gonna put that in my notes. Look at the drawing. Okay, so let's see. I hope all these little lines don't mess with you a little bit. But so that's my drawing that I'm focused on. Okay, so now what do I want to do? I want to take the derivative of this guy, right? I really want y prime, but I have no idea how to take the derivative of the inverse sine function. So I'm going to write it in something that I do know how to take the derivative of. So this statement over here is equivalent to this one, but I can take the derivative of this stuff over here. Like, hey, what is the derivative of x? Or x over 1. Don't need to really think about it as a ratio. It's just plain x. Okay, so the derivative of x with respect to x is 1. Now, we've got a bit of a chain rule here. I've got an outer function, or like layer 1, and then I've got an inner function. I'm going to call that layer 2. So if I take the derivative of layer 1, I get cosine, and I leave the inner function alone. So it's just cosine of y. Then the chain rule says take the derivative of the inner function. So here's layer 2 right now. So here we go, y prime. Now what I'm going to do is I'm going to try to get y prime by itself because that's my goal. I want to find the derivative of inverse sine. So I divide both sides by the cosine of y. So if I divide this side by the cosine of y, and I divide this side by the cosine of y, I end up with y prime equals 1 over the cosine of y. Now, wait a minute. Y prime is the same thing as saying dy dx, right? We've been dealing with a lot of different notation for what is the derivative. And you notice this dx down here. It means I want the derivative of y in terms of x. That's really telling me, that dx down there. But I've got it in terms of y right now. I've got the derivative of y, but it's in terms of y. So I don't want that there. I want to replace cosine of y with what it's equivalent to. Well, the cosine of y is this leg right here over the hypotenuse. Since the hypotenuse is 1, I could really just think about this leg being what I'm looking for. It's the cosine of y. So this leg right here is the cosine of y. So let's do a little Pythagorean theorem. I got a right triangle here. So I go cosine of y squared plus x squared is equal to 1 squared, right? The old Pythagorean theorem, leg squared plus leg squared equals hypotenuse squared. Now I'm going to move the x squared to the other side. I'm also going to square the 1. You're not going to see that 2 up there as an exponent anymore. So I got 1 minus x squared. I got rid of that 2 as an exponent because 1 squared is 1. And then, hey, look, I don't want the cosine of y squared. I just want the cosine of y right here. So what if I took the square root of both sides? Wouldn't that undo the squared on the cosine, right? Hey, there it is. I could do a substitution. I could substitute this stuff right here for the cosine of y because that's what the cosine of y is equal to, right? So, man, I hope I'm making this clear. This is a very tough concept. So I end up with 1 over the square root of 1 minus x squared. Holy cow. There is the derivative. It looks like craziness, doesn't it? It's a fraction, and it's 1 over the square root of 1 minus x squared. Oh my gosh, that's the proof of it. Now, all the inverse trig functions are on page 151. So on page 151, they have something like this written down. The derivative of the tangent, inverse tangent function with respect to x is equal to 1. Oh, geez. I just put some little tick marks on there. 1 over 1 plus x squared. And the derivative of the cosine inverse function, or the inverse cosine function, I should say it that way, with respect to x is the opposite of this guy right up here. So the opposite of 1 over the square root of 1 minus x squared. Okay? And the derivative of the inverse cotangent function with respect to x is the opposite of this guy, the opposite of 1 over 1 plus x squared. So the cofunctions are the same as the original function, just with the negative sign on it. Okay, so we're talking about inverse trig functions today. All right, so the inverse cosine is the opposite of the inverse sine function. The secant function and the cosecant function are the same, just have a negative in them. Look at page 151. Today is a bunch of chain rule problems, okay? So our homework is going to be, starting on page 151. It's going to go to page 152. I put it on Google Classroom. Wow, this is a lot to handle. We're going to try some problems together. Thanks for watching my video and putting some notes down. I appreciate it.